Hello navigators. Today we are going to talk about heat transfer in OpenFOAM. In particular, we are going to talk about conjugate heat transfer, in which we are interested in solving fluid flow in the fluid region and simple conduction in the solid region. Along with that, we want the solid and the fluid phase to talk to each other. How the heat transfer between the solid and the fluid take place, and how we can solve that in OpenFOAM. Today we are going to talk about the theory behind that, and then we'll dive into the setup of these kind of simulations in OpenFOAM. Let's get started. Conjugate heat transfer. It is a coupled solution of heat conduction in solid, as I said just now, and convection and possibly radiation. We'll solve both convection and radiation in fluids. Basically, if there is a wall, and if this wall is at 600 degree Kelvin, this wall will get heated, and if there is a flow which is going above this particular surface, then due to convection there could be some density changes of this fluid that will make these particular molecules lighter. If these particular molecules are lighter, then they will go up, and that will make certain flow which is governed by the temperature difference and density differences in this particular fluid. And there could be radiation as well. For example, you have a surface here, and due to radiation this surface can get heated, and this will again result in some kind of temperature gradient along this surface as well. There are various solvers that are there in OpenFOAM. Some of them are conjugate heat transfer multi-region foam. Clearly there are multiple regions, one is solid and another is fluid, and another with the same name but with a simple foam is for steady state flows. You have to really know that whether your particular simulation that you are currently doing is steady state or not. Then it involves coupling that occurs between fluid and solid interfaces. The boundary conditions that are usually used are temperature of fluid should be equal to temperature of solid, and the heat transfer from this, which is the heat flux from fluid to solid, should be equal to from what is received at this end. The heat transfer should not be generated or lost, so that you should take care of. In the fluid region, we solve these equations which are usual that you see. These are compressible equations. We can see that all the terms are here. The continuity equation, this rho can be variable, rho is not constant, and then you have the momentum equation and the energy equation. In the energy equation, this is one of the term which governs the diffusion of energy in the fluid, and this is the source term. And in the solid region, we usually solve just the conduction equation with this condition that I just described. There are various solvers where you don't solve this. Basically this is for compressible, but you don't have to consider this rho as a variable. You can consider this rho as a constant. That particular assumption is called Boussinesq assumption. This says that there will be change in density that will give rise to a source term that will be added in the momentum equation. This buoyancy terms appears in the momentum equation, and you don't have to solve an energy equation. No full energy equation, only scalar temperature transport. This particular solver we already discussed in our previous lecture, where you can just solve the diffusion of any scalar variable using laplacianFoam, and this can be used for solids and stagnant fluids as well. The boundary conditions are simple. You can have fixed temperature or heat flux. We use both. We had fixed temperature at the cylinder and at the outlet, and all other walls we kept at 0 heat flux. Now let's talk a little bit about the setup for multi-region foam. You have to create two regions if you have something like this. We'll keep on taking this example only, where we'll have a square cylinder and a domain like this. This domain we'll call fluid, and this domain we'll call solid. So there are two regions. Each region has its own mesh and own thermophysical quantity, and in fact its own set of schemes. That means FE scheme and FE solver as well. So you can just solve temperature here, but you can solve for velocity, pressure and everything here. You can have different schemes working in different regions as well. In the interface you can have some boundary conditions. The boundary names are automatically generated, and this is one of the example that you can have a turbulent temperature coupled baffle mixed. You have to solve fluid momentum energy plus solid conduction plus interface continuity. This interface continuity is just the temperature should be uniform across the interface, and the flux transport across the interface, that also should be constant. Now in the fluid you can also have convective heat transfer. This is the equation that governs the convective heat transfer. This is same as the conduction equation. This is an additional term that is due to the velocity of the fluid that you can see here, and this also has a temperature gradient term. This is an additional term that is also solved in the fluid region. You can either do this, which we were just discussing, or this is the temperature transport for incompressible flows, where a Boussinesq assumption is used, that the density variation only adds a source term in the momentum equation. In this equation you can also have another term that is due to the radiation. This is a source term that comes from the heat transfer taking place directly without any source in between that is involved, and you have different models that you can use. So we'll use this model, and along with this surface view factor. If you don't know about view factor, then you can go and read any heat transfer book. You will find this in first or second chapter in the introduction itself. We'll solve these few examples. One will be pure conduction that we have already solved. The second will be the conjugate heat transfer. We'll assume this incompressible fluid along with the Boussinesq assumption, and this one will use the compressible fluid, and we'll solve all the equation along with the energy equation. Then finally we'll solve one final problem where we'll solve the compressible assumption, that is we'll solve the energy equation along with the radiation source term. So the cylinder will emit radiation into the fluid. Probably this will emit radiation and every fluid element will get some heat from this particular source, or these surfaces will get heated. We will see what we'll do in the examples when we set up them. We are going to consider all modes of heat transfer: conduction, convection and radiation. These geometry will remain the same, the 2D square cylinder in the fluid channel. This is the overall summary of that what we have discussed. We have already gone through this laplacianFoam, which is pure conduction. Then chtMultiRegionFoam is used for conduction, convection across fluid solid interface. Here we should note that the fluid here is compressible. We solve the complete energy equation. In Boussinesq assumptions, here we solve the incompressible flow with the Boussinesq approximation, and then we can have a source term added to the energy equation using the radiation models that we discussed, and then we'll solve this in progression. We already solved this. Now we'll solve with Boussinesq assumption, then conjugate heat transfer, and then adding a source term due to radiation. With this, we'll stop here. Thanks for watching, and if you like the content of our channel, then please like, comment, share and subscribe.